My name is Bhupal Day. I'm a senior manager in Telco IBU. I'm here today talking about a project we have done with our customer in North America with T-Mobile. We are partnering with both NVIDIA and T-Mobile for this project. The fundamental goal here is to predict RF signals in terrestrial networks. These networks are very large. Sometimes they will have 100,000 plus base stations. They cover all of North America geography. And the main problem that operators face are really performance optimization, quality, drive tests, predicting signal strength. This is a fairly intense process because real physics from RF networks are involved. You have fairly complex things like reflection, diffraction, and many other phenomena that are really dictated by physics. So what that does is, one is it's very hard to predict, and to actually do the project, very intensive mechanisms are used today, like drive tests. All operators are constantly measured on their quality of their network using drive tests, and this data is publicly available and produced. The challenge becomes operators have to spend a lot of money doing this. So T-Mobile approached us and they asked us, can AWS help using machine learning models do 3D mapping and do prediction of RF coverage models? AWS took it on as a challenge. We were given a particular threshold we had to meet with our modeling capabilities. And to move the project forward, we requested T-Mobile quite a significant amount of data. This included data from user terminals. This included data from terrain. This includes data from drive tests. As AWS, we were able to take all this data and apply machine learning models. I want to talk about something super quick. So what we are showing here on the base layer is a real physical world. This physical world, in terms of radio technologies, is categorized in four different buckets, if you will. You have dense urban environments. This will be Manhattan. This will be LA. Outside of dense urban, there is suburban, and then you have urban, and then you have rural. From an RF propagation standpoint, all of these environments matter, and they differ greatly. In middle of Manhattan, when you have dense urban environments, radio propagation is extremely difficult to map, and it works very, very differently. The spectrum you deploy there is very different than the spectrum you'll deploy in rural. In our case here, we have taken the real physical network, and on the top you see a digital representation, and we call it a digital twin. This digital twin is used for strategic decision making, for analysis, for simulation. Also on the digital twin, we are able to map out real physical phenomena, right? Diffraction, scattering, reflection, and what happens to a radio wave when it goes over water bodies or railroads, phenomena like that, okay? And then what we are able to do with this digital twin is we are able to build a model using SageMaker, and we have done it two different ways. One with AWS and one on partnership with NVIDIA. In both of these models, we have found very high levels of accuracy. We have brought something to the market with our CSP partner that is very accurately predicting signal strength and power for different locations, across the country. So that is the fundamental innovation we have driven here. And what I'll do is hand it over to my colleague Waqar Afzal to cover the details.
Thank you, Bhupal. My name is Mohammad Waqar Afzal. I'm a solutions architect in Telco IBU. I work with North American telecom customers. So I'm going to take you from the problem statement that Bhupal mentioned, how we approach this a little bit deep into the solution. So we took a divergent approach over here that you can see over here. We took the real network data, we ingest that data, and then there is a step 3 over here, and there is a divergent approach. So first approach over here is, since you have all the data from your network that you are taking it, we are taking that data from your real network. We train a machine learning model that will be used for your cell site planning. So how we are doing it? We are taking the data, training a machine learning model. You will give a lat long, and it will be able to tell you the RSRP value that your UEs are going to receive it on that particular location. This will be helpful for your rural areas, urban areas, suburban areas, and dense urban areas. And the biggest thing over here is it is taking the factual data that is coming from your network, telemetry data, user telemetry data. The second approach that we are showcasing over here is that will be more applicable where you don't have any data that is coming from their real UEs. You might want to plan a new location where you don't have a coverage, or you want to do some optimization for your stadium where you're going to have a game and there will be a lot of attendees. So you want to improve the quality of service of your network over there. So in that second approach, we are taking all the physics phenomena, reflection, refraction, diffraction coming from the buildings, from the vegetation, from the lake bodies and all that. We are capturing all those and will be able to tell what is the RSRP values that your UEs are going to get it. And then we are also talking about how much throughput it will get it. You can do a bunch of things over here. You can change the building structure, building material, and it will change the reflection, refraction, and all those phenomena. That's our second solution. And then in the last step, we are going to have the inference. We are going to use some of the services where you can either get it, the inference through the APIs, or you can visualize it, and then you can use it in all your other tools that will be used for your cell site. A little bit more detail on the architecture over here. As you can see, I'm taking the network telemetry data, drive test data, and geoterrain data. You can reduce the drive test data as we will move forward, but you will build a confidence with the drive test data, and then you will completely eliminate it because your end goal is to remove the drive test from your RF planning. That is a costly process. Once you ingest the data, I'm using over here Amazon Kinesis, that is a real-time ingestion service, storing all those data in the S3 as a raw storage. We do a bunch of feature engineering. I'm using AWS Glue over here, where we are doing the feature engineering. We are converting the formats of your geoterrain data from NAD83 to WGS84, raster to digital processing. And then there is a lot of what if analysis, evaluation of all the different parameters that we are getting it, what will be the importance of those parameters towards predicting the RSRP values. So all that analysis, we are doing it in the feature engineering, and then we are training the model using Amazon SageMaker service. Once the model is trained, it will be available, and then we are creating the SageMaker endpoint for the trained models, and then we are using QuickSight to visualize that model. Now, the biggest part over here is you have a network telemetry data that is coming to your network every day. You have weekly data from dive test, and whenever there is a geoterrain change, you can ingest all those data, and with a single click, you can retrain the model, and it will be as updated as you want it to be, so that it will be very precisely able to predict the RSRP values. Second approach that I have described in the previous slide, we are using Amazon EC2 G6E instance that is powered with NVIDIA L40S GPUs. There are 4 GPUs over here, and we are running the NVIDIA digital twin, RAN digital twin on that. There will be one GPU will be used for the front end and one will be used for the back end. Now I come and will explain a little bit on the results. The first approach that we talked about when we were working with our customer, we got every customer, multiple telecom CSP customers have some tools already available in their environment that they are using to predict the RSRP values. The problem with those tools is that they cannot ingest and process the data at scale. You are getting the data at scale, but you would not be able to process it. That's where the AWS cloud computing comes in, process that data at scale, train the model. And when we were working, we got sample set where we want to benchmark our results. So this is what we have root mean square error between the predicted RSRP and the actual RSRP that has been measured at that location. When we did the root mean square error comparison, we got a threshold of 8 dB to meet from our customer. We were able to beat that value, and we were able to predict with the plus minus 5 dB root mean square error. The existing tools, if you see it over here, ripple operators have different type of tools, but the existing tools were able to predict it up to 15 dB plus and minus. And then we have the 3 different frequencies that we used it, where we predicted the results for 3 different frequencies. The second demo that we are going to demonstrate it over here, that demo is powered by NVIDIA L40S GPUs and their ray tracing solution using the digital twin, simulating 3 scenarios over here. During the ray tracing, you can see all the rays, you can see the line of sight that are coming to your UEs from the radio. And then you can see all the reflection, refraction, and all diffusion, absorption type of mechanisms in the visualization. We can also change the building material from wood to glass, and it will change all the reflection, refraction. That will also be demonstrated. And then you can also change the frequency band like 600 megahertz to 3600 megahertz, and it will show you the difference that you are going to get it in your predicted RSRP values. So these are the 3 demonstrations that we have, but this tool can do a bunch of more things. In this demo, as you can see, this is the RF coverage prediction powered by AWS machine learning model. I'm demonstrating the Oxnard area, that is Los Angeles North area. And in each lat and long over here, there are RSRP values that it can predict it. And as you can see, there are CSPs, existing prediction tools. They are predicting the value at this location as neg 81. RSRP value that our machine learning model predicted is 103, and that is 104, and that is very close to the 103. The end product of this one is you will put a point on the map, and at that long, you will be able to see the RSRP value. And moreover, with the what-if analysis, you can put, because you see that there are some, the RSRP values are not good that your UEs are getting, you can pick a point where you want to install your new radio, and you will be able to also see that how it will change the RSRP values by putting the new radio. So that's the machine learning model, and that's the demo for that one. This is the second demo that is powered by NVIDIA. And over here, as you can see, this red one is the radio unit. And then we have a UE over here. You can see 100 these rays that are reflecting and refracting and received by your UE. These are 100 most powerful rays that you can showcase. You are seeing it over here. We can change the number of rays that you can see. And we can, as you can see, this is a Manhattan area in the New York. These are the buildings over here. You can change the building properties over here. Currently it is concrete. You can change it to the glass, and you will see all the values. And on this UE, you can see that what is the uplink throughput it is getting. You can also get the downlink throughput, MCS values, and the other values. Thank you.